we got a pretty extensive list from you about picking the right flow meter.
It can definitely seem a little overwhelming at first.
Yeah, I mean, there's a lot there.
But the goal here is to unpack it all, right? So you can
Yeah.
actually use this stuff.
Yeah, so you come away with like, okay, I can use this. This makes sense.
Practical insights, not just a bunch of jargon.
Yeah, exactly. So you can like actually pick the right flow meter and get it right.
Precisely. It's all about making confident decisions.
Yeah.
When you're choosing a flow meter, it's not just about getting any reading. It's about getting the right reading.
Yeah.
It's a critical component, impacts efficiency, cost effectiveness, all that good stuff.
Yeah, it's like the foundation of everything else.
Exactly.
You mess that up, you're in for a bad time.
Absolutely.
All right, so let's dive right in. The first thing right off the bat is the fluid itself.
The heart of the matter.
Yeah, like what are we actually measuring here? Are we talking about liquid, gas, steam, slurry, or maybe even something, wilder, like a multi-phase flow?
Multi-phase always throws a wrench in the works.
Yeah, it's like that's a whole nother beast.
It really is. And just that initial question, like, what is the stuff we're dealing with? It narrows down your options so much.
Intensely.
It's like, imagine trying to hammer in a nail with a wrench. Just doesn't work.
Right.
Same with flow meters. One designed for a nice, clean liquid. It's going to choke on a thick slurry.
Yeah.
Take ultrasonic flow meters, for example. They work by sending sound waves through the fluid.
Uh-huh.
But if you've got, say, a multi-phase flow with tons of solids or gas bubbles, those sound waves get all messed up.
They get all wonky.
Yeah, wonky. And your readings are going to be way off.
So even if we, okay, we figured out it's liquid, we're not done there, right? Like I'm looking at this list, and the next thing is it says fluid name composition.
Ah, yes. Specificity is key.
Yeah, like we can't just say acid. We got to know, is it 30% sulfuric acid? Is it something else? Why is that level of detail so crucial?
Material compatibility. That's the big one.
Okay.
You got to know exactly what's in that fluid because it's going to be interacting with the materials in the flow meter.
Right.
The parts that are actually touching the fluid. Think about it. You might have some standard PVC that's fine for, diluted stuff.
Uh-huh.
But hit it with a concentrated solvent, that PVC is going to crumble, gone. And we've seen it happen. People overlook this detail and boom, their meter fails, starts leaking, maybe even causes a safety hazard.
Not good.
Not good at all. Costly downtime, repairs, you name it, all because they didn't know exactly what they were dealing with.
Right. Okay, moving on. We've got viscosity. And we need to specify a range here, minimum and maximum, usually in centipoise or centistokes.
It's the stickiness factor.
Yeah, and I'll admit, this one always kind of trips me up. Like, what is viscosity in simple terms? For those of us who aren't, like, fluid dynamics experts.
Okay, think of it this way. Viscosity is like a fluid's internal friction, how much it resists flowing.
Okay.
Honey, super viscous. Water, not so much.
Makes sense.
And for certain flow meters, like positive displacement meters or turbine meters, viscosity really matters.
Yep.
If the fluid's thicker than what the meter's calibrated for, it might read too low. If it's thinner, it might read too high.
Got it. So we got to make sure the meter's designed to handle the viscosity range we're working with.
Exactly. And here's the thing. Even small temperature changes can mess with viscosity.
Really?
Oh, yeah. So if you've got a process where the temperature fluctuates, you got to factor that in. Otherwise, your viscosity readings could be all over the place, and that throws off your flame measurements.
Interesting. So like even a small temperature change can have a huge effect on the viscosity and therefore the measurement.
Exactly. You got to be mindful of the whole picture.
Okay, so we've got, how thick it is, that's viscosity. Now we've got density and specific gravity. Again, a range is needed, especially if temperature and pressure are going to be changing. Why is this info so important?
Well, density, it tells you how much mass you have in a given volume. Like how heavy is that fluid?
Okay.
If you need to figure out the mass flow rate, density is your friend.
Right, because a lot of flame meters measure volumetric flow, like liters per minute.
Exactly. So you need that density data to convert it to mass flow, like kilograms per hour.
Makes sense.
And some flow meters, like Coriolis flow meters, they actually measure mass flow directly.
Oh, cool.
Yeah, by looking at the fluid's inertia, which is tied to density. But here's the thing. If you're working with gases, density can swing wildly with changes in pressure and temperature.
Oh, right.
So knowing that operating range is super important for getting accurate mass flow calculations.
Okay, so we've got the thickness with viscosity, and now we've got the heaviness with density. All important stuff.
Building block.
Yeah. All right, next up is operating temperature range. minimum, normal, and maximum. What are we thinking about here when picking a flow meter?
Well, remember how we talked about temperature affecting viscosity? It also impacts the flow meter itself.
Uh,
Those materials inside the meter, especially seals and gaskets, they got to handle the whole temperature range without falling apart.
yeah, we don't want any meltdowns.
No meltdowns. And the electronics in the transmitter can be sensitive to temperature extremes, too.
Oh, interesting.
Yeah, it could lead to bad readings or even damage the thing. So you got to make sure that meter is rated for the full temperature spectrum of your application.
Gotcha. So it's not just about the fluid, it's about the meter itself being able to handle the heat, so to speak.
Exactly. It's got to be up to the task.
Okay. And speaking of handling things, next we've got the operating pressure range. Minimum, normal, maximum. This one feels pretty straightforward, right? We just got to make sure the meter won't explode.
You got it. The meter body has to be strong enough to handle the maximum expected pressure, no leaks, no ruptures.
Safety first.
Always. By specifying the pressure range, you're making sure you get a meter that's built tough enough and meets all the safety standards.
All right, now we're getting into some specifics. We've got conductivity, and this one's just for liquids. We mentioned magnetic flow meters earlier, where you need at least 5 microsiemens per centimeter.
Right. Conductivity is all about how well a liquid can conduct electricity.
Huh.
And for mag meters, it's essential. They work on this principle called Faraday's law of electromagnetic induction.
Sounds fancy.
It is a bit fancy. But basically, as the conductive fluid flows through the meter, it creates a voltage.
Okay.
And that voltage is proportional to the flow velocity. But if the conductivity is too low, the voltage is super weak and the meter can't get an accurate reading.
Ah, so it's like the fluid needs enough juice to make the meter work, right?
Pretty much. It's a fundamental requirement for that technology.
No conductivity, no reading. Got it. Next up, corrosiveness and abrasiveness. These seem like they would really dictate what materials we could use inside the flow meter.
They absolutely do. If you've got a highly corrosive fluid, forget about using standard stuff like carbon steel.
Yeah, that's not going to end well.
Nope. You'll need some serious chemical resistance like stainless steel alloys, hastaloy, maybe even special polymers.
Right, right.
And abrasiveness is a whole other challenge. Those particles in the fluid, they can wear down the meter's insides over time.
Like sandpaper.
Exactly. So you might need hardened liners or special designs that protect the meter from those abrasive forces.
Makes sense. All right, now this next one seems kind of related. Presence of solids and particulates. You mentioned clogging and interference too. What should we be thinking about here? Like size, concentration, hardness of those solids?
All those things matter. Big chunks can physically block the flow path, especially in meters with narrow passages.
Oh, right, like a clogged pipe.
Exactly. And even if the solids are smaller, if there's a lot of them, they can interfere with the meter's sensing mechanisms, like in ultrasonic or optical flow meters. And as we talked about with abrasiveness, the hardness of those particles will determine how quickly they wear down the meter.
It's all connected.
It is. And for fluids with lots of solids, you might consider designs that are less prone to clogging,
Right.
like magnetic flow meters or certain types of ultrasonic meters.
Okay, last one in our fluid properties marathon. Vapor pressure and potential for flashing. This sounds particularly relevant for liquids that are close to boiling, right?
It is. Flashing is when a liquid suddenly vaporizes and forms gas bubbles because the pressure drops below its vapor pressure.
Okay.
And if that happens inside a liquid flow meter, it's bad news.
Yeah, that doesn't sound good.
Most liquid flow meters are designed for, a continuous liquid phase. Throw in some gas bubbles and your readings are going to be way off.
So we got to be mindful of vapor pressure and make sure the pressure inside the meter stays balanced.
Keep those liquids in liquid form.
All right, we made it through the fluid properties gauntlet.
We survive.
Now let's shift gears and talk about flow conditions and installation. First up, flow rate range. Minimum, normal, maximum. You mentioned this is key for sizing and figuring out the turndown ratio. So what is turndown ratio and why is knowing the flow rate range so crucial?
Okay, turndown ratio is basically the range of flow rates the meter can accurately measure. It's the maximum flow rate divided by the minimum flow rate.
Okay.
And you need to know your expected flow range to make sure you pick a meter with a wide enough turndown ratio to cover all your operating conditions.
That makes sense.
Like if your flow rates jump up and down a lot and you have a meter with a narrow turndown ratio, it might only give you good readings in a small part of that range. And at the high or low ends, it's going to be inaccurate, which could mess up your process control.
Right, right. So we got to make sure the meter can handle the full range of flows we're going to see.
Exactly. It's all about having the right tool for the job.
Okay, next up, units of measurement. This seems basic, but it's clearly important to specify whether we need GPM, LPM, MROR for volume, or, SCFM, LBHR, KAGS for mass flow. Why is this seemingly obvious point worth highlighting?
Because a mismatch here can cause a whole lot of headaches later on.
Oh, yeah.
Imagine your control system needs a mass flow rate in kilograms per second,
Okay.
but you accidentally specified a volumetric flow meter without thinking about density compensation or direct mass flow measurement.
Uh-oh.
You're going to end up with the wrong data, and that can lead to all sorts of problems.
Right. So being clear about units from the start is crucial.
Absolutely. It's like speaking the same language as your equipment.
All right, now let's talk about the flow profile. Steady, pulsating, intermittent, highly variable. How does this affect our meter choice?
Well, different flow meter technologies handle different flow profiles better.
Yep.
Like positive displacement meters, they're pretty good with pulsating flows. But other types, like differential pressure flow meters, they might struggle if the flow is jumping around too much.
Got it. So we need to match the meter to the personality of our flow, so to speak.
Exactly. You got to know what you're dealing with.
Okay, and speaking of personalities, we've got flow direction. Unidirectional or bidirectional? Can all flow meters handle flow going both ways?
Nope, not at all. Some are strictly one-way streets.
Oh.
So if you've got a process where the flow might reverse, you got to pick a meter that's designed for bidirectional measurement.
Makes sense. Otherwise, we're only going to get readings half the time.
Exactly. You need a meter that can handle the flow no matter which way it's going.
All right, let's get into the physical installation. Pipe size and schedule material. Why do we need to know the internal diameter and all that stuff about the pipe?
Well, the pipe size determines the size of the flow meter you need. Got to make sure it fits right.
Okay.
We don't want any bottlenecks or leaks. And the pipe schedule tells you about the wall thickness and pressure rating. Got to make sure that's compatible with the flow meter's connections and the pressure in the system.
Right.
And the pipe material itself can be important too, especially if you've got different metals that might corrode each other.
Interesting. So it's not just about shoving the meter into any old pipe?
Nope. It's all got to work together harmoniously.
Okay, this next one I hear about all the time. Available straight run. You mentioned needing enough straight pipe both before and after the meter. Why is that so important?
A lot of these flow meter technologies are picky. They need a nice, smooth, predictable flow. Bends, valves, pumps, all those things create turbulence and swirl, which messes up the flow pattern.
Okay.
And if you don't have enough straight run, the flow going into the meter is going to be all wonky and your readings will be off.
So it's like giving the meter a clear runway.
Exactly. Let it do its job without any distractions.
Makes sense. All right, what about pipe orientation? Horizontal versus vertical, and if it's vertical, which way is the flow going? Does that matter?
For some flow meter types, it can. Like some older designs or specific types might have limitations.
Oh.
For example, some variable area flow meters, they work with gravity and are meant to be installed vertically with upward flow.
Interesting.
A lot of modern flow meters are less picky about orientation, but it's always good to double check the manufacturer's specs.
Right. Better safe than sorry.
Exactly.
Okay, moving on to connection type. Flanged, threaded, wafer, sanitary insertion. Sounds like a lot of options. How do we pick the right one?
Well, it's got to match your piping system, for one thing.
Okay.
And it's got to meet any industry standards. Like if you're in food and beverage or pharmaceuticals, you need sanitary connections.
Right.
And then you've got things like pressure rating, ease of installation, maintenance, all that good stuff.
So there's a lot to consider.
There is. It's all about finding the right fit.
Okay, last one for installation. Available space. This seems like common sense, but I guess it's easy to overlook.
It is. But you got to make sure that meter actually fits in the space you have and that you can access it for maintenance and calibration.
Right. We don't want to install it and then realize we can't reach the darn thing.
Exactly. Don't underestimate the importance of a little elbow room.
All right, we've covered fluid properties, we've tackled installation. Let's move on to performance, output, environment, and budget.
Fun stuff.
Yeah. First up, accuracy. We got to specify how precise we need our measurements to be. Maybe plus or minus 1% of reading or plus or minus 0.5% of full scale. You mentioned that higher accuracy usually means a higher price tag.
It's true, those super accurate flow meters, they've got fancier tech and stricter calibration, which drives up the cost.
Okay.
So you got to think about what level of accuracy you really need.
Right, right.
For some applications, a less precise measurement might be totally fine.
Yeah.
But if you're doing critical process control, custody transfer, anything where you need really tight numbers, then yeah, you got to shell out for that higher accuracy.
Gotcha. So it's all about balancing cost and need.
Exactly. Precision comes at a premium.
All right, next is repaintability. You said that consistent measurement is often more important than absolute accuracy, especially for control applications.
It's true. Repeatability means the flow meter will give you the same reading under the same conditions time after time.
Okay.
And in control systems, it's all about reacting to changes in flow.
Right.
So even if the absolute reading is slightly off, as long as the meter consistently shows changes, the control system can do its job.
Makes sense. It's like the system doesn't need to know the exact number, just how much it's changing.
Precisely. It's all about relative changes, not absolute values.
Okay, next we've got allowable pressure drop. This is about how much pressure the meter itself is going to lose.
Yeah, anytime you put something in the flow path, it's going to cause a pressure drop.
Okay.
Some flow meter types, like orifice plates, they cause a bigger drop than others, like magnetic flow meters. And that pressure loss means you need more energy from your pumps or compressors to keep things moving.
Which costs more money.
Exactly. So you want a flow meter that gives you the accuracy you need without creating a huge pressure drop.
Right. Got to find that sweet spot.
Balance is key.
Okay, now we've got response time. This is about how quickly the meter reacts to changes in flow rate, right?
Yep. If your flow rates are jumping up and down a lot, you need a meter that can keep up.
Yeah, otherwise it's going to be lagging behind.
Exactly. A slow response time can mess up your control loops, causing instability and all sorts of problems.
So the response time needs to be appropriate for how quickly things are changing in the process.
Exactly. It's got to be fast enough to keep up with the action.
All right, let's talk about how we get data out of the meter. Required output signal. We've got 420 MA, pulse frequency, digital communication protocols. How do we choose?
It all depends on what kind of system you're connecting the meter to.
Yeah.
420 MA is a common analog signal for transmitting process variables. Pulse frequency signals are often used for totalization or for certain controllers. And then you've got digital protocols like HART, Modbus, Foundation Field Bus. They offer more advanced communication.
Gotcha. So you got to make sure the output signal plays nice with our existing setup.
Absolutely. Compatibility is key.
Okay, what about a local display? Do we always need one on the meter itself?
Not necessarily, but it can be handy for monitoring, troubleshooting, and calibration.
Yeah, I guess it depends on how accessible the meter is.
Exactly. If it's buried in some hard-to-reach spot, a local display can save you a lot of hassle.
Makes sense. And totalization is pretty straightforward, right?
Yeah.
If we need to track the total amount of fluid that's passed through, we need a meter that can do that.
Yep. Essential for things like batch processing, inventory control, stuff like that.
Okay, moving on to power availability. We got to know what's available at the installation point, right? Loop-powered AC/DC.
Right. The meter and its transmitter need the right kind of power.
Makes sense.
Loop-powered devices can simplify wiring, but other devices might need a separate AC or DC supply.
Okay, so got to match the meter to the power source.
Exactly. Can't run a DC motor on AC power.
Now we're getting into environmental factors, ambient temperature range. We talked about the fluid temperature, but the surrounding air temperature matters too, right?
Absolutely. Those electronics in the meter and transmitter, they have their own temperature limits.
Yeah.
Too hot or too cold, and they might start acting up.
Gotcha. So we got to make sure the meter can handle the climate.
Exactly. Got to keep those electronics happy.
All right, next up, hazardous area classification. All those scary acronyms. Class I, Div 12, Zone 012, ATEX IESEX. What's the key takeaway here?
These classifications tell you if there's a risk of explosion because of flammable stuff in the air.
Oh, okay.
And if your meter's going in one of those areas, you absolutely got to choose a meter that's certified for it.
Yeah, that's not something you want to mess around with.
Nope. Safety is paramount. Using the wrong equipment in a hazardous area can have catastrophic consequences.
No explosions, please.
Definitely not.
Okay, we've also got ingress protection, those IP or NEMA ratings. This is about how well the meter is protected against dust and water, right?
Yep. The rating tells you how well the enclosure keeps stuff out.
Okay.
So depending on how dusty or wet the environment is, you need the right IP or NEMA rating.
Right. Like a meter in a dusty factory would need more protection than one in a clean room.
Exactly. It's all about matching the protection to the environment.
Okay, and then we've got regulatory approvals. Things like custody transfers, sanitary drinking water approvals. Those seem pretty specific to certain industries.
They are. Certain applications have strict rules and regulations.
All right.
Like if you're measuring fluids for sale, you need custody transfer approvals.
Uh-huh.
Food and beverage, pharmaceuticals, they need sanitary approvals.
Right. Got to keep things clean.
Absolutely. And drinking water systems have their own specific standards.
So it's all about making sure the meter meets the legal requirements.
Exactly. Got to stay on the right side of the law.
Yeah. All right. Finally, we've made it to budget and maintenance considerations. Obviously, the purchase price matters,
Of course.
but you've also emphasized thinking about the long-term costs.
Absolutely. The initial price is just one piece of the puzzle.
Right.
You got to think about calibration, maintenance, how likely it is to get clogged or wear out, how long it's going to last.
Yeah, that all adds up.
It does. Sometimes a cheaper meter ends up costing you more in the long run because it needs constant attention.
So it's about looking at the total cost of ownership, not just the sticker price.
Exactly. It's a long-term investment.
All right, wow. We covered a lot of ground today. Denny from Pakistan Controls
Yeah.
and Industrial Automation here. And I got to say, that was a deep dive into Flowmeter specifications.
It was a journey.
It was. And I think the key takeaway is that there's a lot to think about.
Absolutely. Choosing the right flow meter is about more than just picking one off the shelf.
Yeah, you really got to understand the fluid, the application, the environment, everything.
You got it. And by taking the time to consider all those factors, you'll end up with a meter that works reliably and accurately, giving you the data you need to run your process efficiently.
Absolutely. So thinking about all this, what do you think is the single most overlooked specification? Like, what do people often forget about that can come back to bite them? That's something for you all to ponder. And for more information on all things industrial automation, you know where to find us. PAKCIA.com, the Pakistan Controls and Industrial Automation website. Thanks for joining us today.
Until next time.